All right, welcome everyone. So let's try a little bit of practice with these ideas relating to, in particular, column space of a matrix A here. So we've been working with a question of, here's a matrix A, tell me what the column space is. This is kind of the reverse of that question. So here we're given what the column space of some matrix A is, and we'd like to find a matrix A that has this column space. So let's do this in a couple of steps. So the first step here is let's go ahead and write out matrix A as a linear combination of some vectors. So for example here, we could go ahead and write out matrix A as X times the vector 1, 0, 1 plus Y times the vector -2, 3, 1, where X and Y are any real numbers. Okay, now for the second step, now that we've got these two vectors above, let's use these two vectors that we have in the spanning set, and we're going to use them as the columns for this matrix A that we construct. So now I can take some matrix A, and its first column is going to be the vector 0, 1, 0, and the second column will pick -2, 3, 1. And we can see here that the column space of A would equal the span of these two column vectors, right, which is exactly equivalent to the set that we started with. So a matrix such as this one, this is a 3 by 2 matrix, the top row 1, -2, second row 0, 3, and the third row 1, 1. Here's a matrix A whose column space would equal exactly this set of vectors that we had initially. Okay, so let's summarize some of these results that we've seen for null column and row spaces for an M by N matrix A. So if we have a matrix A which is M by N, we are thinking about this as a map from Rn, the number of columns in the matrix, to Rm, which is the number of rows in the matrix. So our domain here is Rn, which is, again, the number of columns that our matrix has, and the codomain is Rm. And I want to refer back to this example that we've been working with, where we started with A being a 2 by 5 matrix. The top row was 3, 6, 6, 3, 9. The second row was 6, 12, 13, and 0, 3. And we were able to do some row operations, or using Python, identify the reduced row equivalent form of this matrix, which had a top row of 1, 2, 0, 13, 33, and a second row of 0, 0, 1, -6, 15. And there was something significant about the pivots and the free variables in the reduced row echelon form of this matrix that connected to finding the null and the column space relating to matrix A. So let's kind of review those ideas. So the null space A is a subspace of the domain. Okay, so the domain is Rn. And the way that we can find the null space is we put it in its reduced row echelon form, and then we can identify the free variables like x2, x4, and x5 were free variables. And then we were able to write out the solution set of this space. And then from that solution set, we found the vectors that spanned the null space. For the column space of A, we noticed that there were two pivots on this matrix when we put it in reduced row echelon form, and that corresponded to pulling off the first and the third columns of matrix A, which gave us a spanning set for the column space of A. So the column space of A is spanned by the original pivot columns of matrix A. And so there were two vectors that we needed to construct the column space of A. There were three vectors that we needed to form the null space of A. And adding those together, we get the full 3 plus 2 gives us all 5 columns of matrix A.